So welcome to our big data class for today. We're going to today talk about your last homework assignment in the class, the search engine assignment. We'll talk today about pretty much everything that you need to complete the assignment, but then on Wednesday this week and Monday next week, we will talk a little bit more about some of the underlying techniques that are going on behind the scenes in this search engine that we haven't fully talked about yet. So we've talked a lot about indexes. That's going to be very important in this assignment, making this search engine fast. But there's also something called a materialized view and a roll-up table. And I've used those words once or twice in previous lectures a long time ago, but we haven't really talked about those in detail. And that'll be what we'll do on, I guess, the next two lectures. And then, we only have, after today, 3 more lectures. So the very last lecture of the class will essentially be like a review for the final lecture. Any questions about kind of what to expect from the last 2 weeks in terms of that? Okay, then so we're going to talk about the assignment today. That'll be the main part of today. But before doing that, I want us to talk about one of the previous assignments and going over some of the answers. So I will share my screen here. And I'm currently on our week 13 folder in the GitHub repo. And in this folder, I've added an answer key to the week 9+10 PDF file. So it was a while ago that we first assigned this, this assignment, but there was a handful of extensions for a handful of different reasons. And so now's the first time that we'll have a chance to talk about the answers. And one of the main reasons that I want to talk about the answers is because the scores on this assignment were pretty disappointing from my perspective. And the assignment is going to be very reflective of the types of material that will be on the final exam. So there's currently a lot of good grades in this class. I hope there will continue to be good grades in this class after the final exam. But in order for that to be the case, I think a lot of people will need to improve your understanding of this homework assignment in particular. I'm going to switch my screen over to the answer key of this file right here. And so recall that this assignment was the PDF assignment where at the top I gave you a bunch of true and false questions and you weren't required to do anything with those. But again, those will be reflective of the sort of questions you'll get on the final exam. And then this second half right here is the actual graded portion of the homework assignment. And I want to highlight a lot of the sort of common mistakes that people made here so that hopefully you won't make them again on the final exam. So first of all, in this first problem right here, I was asking you to list the different indexes that were created. And the particular things that I was looking for each one of the indexes is what is the table that the index is created on, and what are the columns that the index is created on that particular table. And there were a lot of different ways that you could sort of present that information. Any of those ways was fine as long as the information itself was correct. So some people chose to actually write out a create index command. That's perfectly okay. Some people just did like what I have here. This is sort of the minimum bare bones thing. But the main, the main mistake that people made on this assignment was with this references keyword with these foreign keys. And the main mistake was that people assumed that if you have this references keyword, that Postgres is going to create an index for you on both the target table over here to the right of the references and the source table and column to the left of the references. And that's not true. That Postgres will only create the index on the target of a reference. Will not automatically create an index for you on the source of a reference. And in this particular case, the indexes created by the primary keys are actually the only indexes that get created, because all of the references point to a column that already has a primary key created on it, either users id users or tweets id tweets. So these are the three indexes that get created. And this is a sort of really fundamental concept that that other concepts will build on. So on the final exam, a question like this, you need to be 100% sure that you get this question correct. Let's see, I'll occasionally stop for questions, but I'll mostly just kind of go through this. And so if you do have questions, feel free to interrupt me at any time and ask whatever your question is. Let's see, problem number 2. So 2 was sort of
I have a quick question.
Go ahead.
So, I mean, not exactly about this question, but I was just looking up stuff about Postgres and how it creates indexes. And wherever I looked, it said that it doesn't create indexes on foreign keys, like on like foreign key or like references and stuff. So I wasn't really completely sure like when it actually creates references and when it doesn't, because yeah, I just wasn't sure.
So the 2 rules are that every primary key will get an index, and in particular a unique index. And then every time there's a foreign key, there's a reference on the target, but not a reference on the source. So here, when it says references right here, there'll be an index created on users, ID users. In this case, there already is an index for users, ID users right here. So there's no need to create a new one. There's no index for tweets, ID users right here. So it will not create that though, because it's to the left of the references. It's the source of the foreign key rather than the target of the foreign key. And so when people talk about Postgres not creating indexes for foreign keys, that's what they're talking about, is there'll be no index on this id users right here.
Okay, I see. That makes yeah, just a little confusing.
Yeah. And yeah, totally okay to be a bit confused about these sort of things, because there is a lot of different things going on, and they're all potentially very subtle things. And so speaking of subtle, we'll go on to problem number 2 right here, which is I think a very subtle sort of problem. And this is one of the common problems that a lot of people missed, even if you otherwise did really well on the assignment. So here, it's asking you to list the scan methods applicable for the following SQL query. And the first thing to point out is that when it says what scan method is applicable, that's different than asking what scan method is actually used. That, if you recall, the Postgres query planner, it has many different algorithms that it can choose from. And some of those algorithms are applicable, allowed to be chosen in certain situations. But when it actually executes the query, it's only going to pick one of those allowed algorithms. When I'm asking for applicable, it means you have to list out all of the possible choices that could have been taken. So I think a number of people tried to create your Docker container, like I recommended, with this code in the container for your schema. And then you use the explain or explain analyze command to figure out which query algorithm is actually going to be used in practice. And that doesn't work, because that will only ever give you a single result, and you need potentially multiple results. So anytime you see something like applicable, explain is not going to be a sufficient thing to do. In general, the particular choice of an algorithm is going to be highly variable and depend on the actual contents of the table. And so I'm not going to ask you to try to predict, is it going to do a bitmap scan or an index scan, because we just can't know that without knowing information about the data. So anytime I'm asking you like what scan methods, anything about scan methods or anything about join methods, it's always going to be what are just the applicable ones, what could it be chosen? And so explain is not going to be super useful for that question. So it's the first point about both number 2 and 3 here. The second point about why this one is tricky is that, so here, if you saw, instead of saying from tweets where this condition, if it said from users where this condition, then it would be every scan method is applicable. And a lot of people listed every scan method as being applicable. I think probably from just not a super close reading of this, mixing up this tweets table with the users table. Looking back up here, we have tweets, id tweets, users, id users, but there's no tweets, id users. One of the ways that, so that was one way that people sort of made that mistake, got that confusion. Another way that people made that mistake is if you, for your foreign key, all of these references, if you said that Postgres is going to make an index on the source column and listed that down here, then that would have, that index, which doesn't actually exist, would have enabled you to do all of those scan methods. But because that index doesn't exist, you can't do those scan methods. So that's why this is a particularly important sort of question to get right, because other questions are going to depend on it. And because this question is so important, I will count that as like double jeopardy against you. You really want to make sure that you understand what indexes are in your database at any given time. That's like the most fundamental thing to understand about getting your queries fast. Yeah, so that's number 2. Number 3 is similar. Here we have 2 columns that are being selected for. And in particular, there's this username column. We have an index that corresponds to the table users and id users. So we can do our index scan, bitmap scan, but we cannot do the index only scan because of this extra column right here. So these are the 3 applicable methods. For number 4, people tended to do well on this problem. The key idea here is that when we have this search right here, this select statement, and we have id users as our condition, we want that to be the very first or leftmost column in our index that's been created. And the indexes that were created for us automatically had id users as the rightmost index. So we can't efficiently do an equals condition on that. And so that's why creating a query, something like, or creating an index, something like this is important. A handful of people who did create a correct statement like this said something really bogus in your in an explanation, and I counted that against you. Anytime on any of these answers, if you said something that was just incorrect in some way, then you lost the points for that problem. So it's important not to write too much stuff in the sense that you write stuff that ends up being incorrect. You want to make sure that your words are precise and correct as possible. For number 5, the similar sort of index, multi-column index down here, and the key idea was that you had to get the order of these columns correct. That anytime you have, again, an equals condition in your where clause, those equals conditions need to be to the leftmost spot in your multi-column index for it to be correct. A couple of people chose, instead of creating a single index like this, chose to create multiple indexes, one on id users and a separate one on created at. And I agree that would speed up a query like this. Then you could do a, say, a bitmap scan. But the problem is specifically asking for an index-only scan. And anytime you're doing an index-only scan, it can only do it on a single index. The only scan method that can work with multiple indexes is the bitmap scan. Number 6, relatively similar. It's just adding this one more field to the index down here because there's one more field up here. It's not explicitly asking, oh, I guess it is explicitly asking for the index only scan right here. But as long as, if you're doing this index only scan, that is a not a necessary, but a sufficient condition for these other two clauses, avoiding an explicit sort and taking advantage of the limit clause. If you're doing an index only scan or an index scan, you get those two things for free. It's when you're doing a bitmap scan that you don't get the explicit sort or the limit clause advantage. For number 7, the see, a lot of people missed this problem, either saying that no index was needed because there was already a unique index on the users table. And it's true that there is a unique index on the users table, but it's on the id users column and not the username column. And so you would still need to create a unique index on the username column. It's also important that you only have the username column in this column list right here, because if you also included the created at, then it would be perfectly fine to have multiple usernames that match each other as long as their created at field is different. And so we don't get any real actual verification of usernames being unique. This is the correct syntax in order to ensure that unique index on username, but still able to do an index only scan, still including this created at information in the index itself. For number 8, the main I guess trick for number 8 is that you have these 4 columns, and they just had to be in the correct order. It's possible to explicitly specify that certain columns are ordered ascending or descending in here. Depending on your actual data, that may or may not help your performance. And so it wasn't basically no matter what you put for ascending and descending, didn't matter. You could have left those off entirely and it still would have been a fully correct answer. For number 9, I think people tended to do well on this one as well, that there are no new indexes required for this one, that we already have a good index for tweets mentions and already have a good index for tweets. And so you don't need to create a new index. A handful of people chose to create a new index on the, whoops, I have an old version of this file loaded right now, not on tweets, id tweets, but on tweets mentions, id tweets. A handful of people chose to create that index. And the reason is, if we come back here to the indexes that are created, we already have this tweet mentions on id tweets with the leftmost column, but there's always already an id users here. And so like we talked about in class, that's going to cause us to add more information into each page or each tuple stored in the index. And so fewer tuples were stored in the index, so the fan out will be smaller, so more pages will be needed to access in order to get down to the leaf node of the index. And so it would, the indexing would likely be a little bit faster if we had an index without this id users inside of it. So you got full credit either way, whether you created a new index, that particular index or not. In practice, in a real world scenario, there's not an index that you would want to create, that the difference in performance between those two indexes on a read is going to be 1, maybe 2 page files from the index that'll have to get read. But every time we do an insert or an update delete, that's going to add a significant amount of overhead of probably 5 to 10 page files that'll have to be updated on each of those operations, plus making vacuum more expensive because we have more things to vacuum now. So in the real world, you would never add, you would only have one of these indexes. But for the purposes of this question, either solution was correct. For number 10, these were the two indexes that were correct. A handful of people provided slightly different solutions as well that were okay, and I give you full credit for those. But the key thing for these is again the order. That the order of these indexes is really important, or the order of the columns in the index. For number 11, a lot of people, let's see, a lot of people put the right answers of this first index is going to both be the fastest and use the less space, but a lot of people had sort of really bogus reasons as to why that's the case, and so you did not get the full credit on due to your explanations. And so there are two reasons why both of these tweets index 1 is the correct answer for both of these statements. And if you provided either of these reasons and nothing incorrect, then you got full credit. You did not have to provide both. But first of all, it's a partial index right here. So because it's a partial index, it's not going to include any extraneous information in the index. And so the height of the index will be shorter. And so you'll have fewer pages that you have to access to go from the root to the leaf. So that's the first reason. And then the second reason is that it's a single column index instead of a multi-column index. And so like we mentioned in one of the previous problems, when you have a single column index, you can store more tuples per page. So your fan out is larger, so the height of the tree is smaller, so you access fewer pages when you go from the root to the leaf. If you said either of those two things, then you got full credit on this. And the least amount of disk space is the same answer here. The last questions, let's see. You were not required to provide any explanation for these questions, and you would have gotten full credit if you provided no explanation. But again, this is a spot where some people said things that were just incorrect. And if you say something that's incorrect, it will count against you. So here for the sequential scan, it's going to increase because you'll have more data per tuple. And so that implies you'll be able to fit fewer tuples per page, and so you'll have more pages to store the same number of tuples. And so the sequential scan, because it must visit all pages, will have to visit more pages. One of the sort of main ways that people, I think, lost points for the sort of bogus answer reasons is you got confused about the definition of a tuple versus a page versus a relation, and you're saying, in some instances, using the word tuple to refer to the idea of a page, or using the word relation to refer to the idea of a tuple. And so because of that, your explanation was way off. So you need to make sure that you have those definitions down when you're on the final and writing these sorts of things. For the index only scan, it's going to stay the same because the adding more information into the table itself is going to bloat the table, make the table, the pages in the table, more pages in the heap portion of the table, but it doesn't affect the index at all because these other columns are not contained in that index. And so that'll stay exactly the same. For an index scan, I selected or I accepted two solutions, either that it stays the same or that it goes up. The reason you could say that it stays the same is that in an index scan, the tuples are not returned in any sort of sorted order. So if we get 100 tuples returned, we have to check each page for each one of those tuples. even if we've already checked that page before. So the fact that the tuples are spread out over more pages doesn't really matter because we still have to check one page per tuple. So that's the justification for staying the same. The justification for it increasing is that if you didn't consider accessing the same page file as multiple times, if you didn't consider that as distinct accesses, but as just as one access, then there'll be an increase in the number of distinct pages that you access. And that's for a bitmap scan, that's very important because we're guaranteed to access each page exactly once in a bitmap scan, whereas in an index scan, you can access the same page multiple times. So for a bitmap scan, for that reason, increase is the only acceptable answer. Again, I think most people did reasonably well on the getting the directions right. It was just the explanations that lost points on. One other big picture concept that a lot of people did not, or that a lot of people had trouble with, is when we say have a query like this, where there is the colon blah, so in this case colon username in the query, that is something that is provided by the user somehow during the query. And so that could be any value. The username could be Mike, it could be is Vicky, it could be Evan, it could be Kristen, it could be any possible value. And we don't know that in advance when we're creating the index. So it's impossible to create a partial index where the condition in the where clause is based on this colon username, because we don't know what that is. It could be anything. And when we create a partial index, we must know in advance what that is. Yeah, so a lot of people lost points in various problems for creating partial indexes on these user supplied conditions, which you can't do. So yeah, that's the summary of the answers to these questions. I would strongly again recommend that before the final exam, you feel like you have 100% understanding of why these are the correct answers and how you can put down correct answers on similar problems on the final exam, because you will have similar problems to these on the final. Are there any questions about anything related to this homework assignment?
Sort of. This is, like, you mentioned it, like, very briefly when you're going over the questions, but I always keep getting mixed up. When we're talking about foreign keys, which table is the source table and which table is the target table?
Let's see. At least when I've been using the word source and target, to the left of references is the source, to the right of references is the target. That's probably not, that may not be 100% standard convention. Some people might do it different, use those terms differently. Those are definitely not terms that are like in the Postgres documentation. But I think that's what most people mean when they say source and target. So to the left is the source, and to the right is the target. And it's the thing that's to the right that Postgres creates the key on. And the reason it creates that key is because when it's enforcing this foreign key constraint, it needs to be able to efficiently access. So when we insert into tweets, insert a value here into id users, say 27 is the value that we insert into id users. In order for Postgres to ensure that that is correct, it needs to be able to efficiently find an id users inside of the users table that has that same column or that same value. And if we did not have a key, and this table here was multiple terabytes large, then a single insert on this table would require scanning multiple terabytes of data on this table, which would take a very long time. And so that's why Postgres will automatically create keys for you on the target table, because that greatly speeds up the inserts into this table here. there are some situations where having a key on your on the source column over here is also going to speed things up, but those situations are much more rare. And so Postgres assumes that if you are in one of those situations, that you're going to know that and take care of that key for yourself. But the insert, update, delete, those happen all the time, and so that's why Postgres makes that key, that index for you automatically when you have a foreign key. Good question. Any other questions about the assignment?
I had a question about question 10.
Sure.
So do we need to have id tweets and tweets mentioned in the index for tweets mentioned?
No. So if you did not have, this was one of the problems. There's a handful of different correct solutions to this problem. If you did not have id tweets right here, only had id users in your tweets mentions, then that's a perfectly valid solution. You shouldn't have lost points for that. Let's see. So the reason for including id tweets is that by including it, we won't need to actually go back and access the table necessarily in order to get these id tweets values right here. And so previously to the join, when it's getting the information out in sorted order, it could do an index-only scan, grabbing both of these values from the index in sorted order and joining on that. It's not guaranteed to, but it's allowed to. Yeah, so either way, you'd get essentially the same speed up, and so both are correct. Good questions. Any other questions?
Just to be clear on like questions like these, are they all one question in terms of like if you create an index and say problem 9, does that index still exist in problem 10?
Yeah, it's a good question. So either way, however people answered, whether you assumed the previous indexes existed or didn't exist, then either way was acceptable. When I was writing out the solutions here, I was doing it assuming that the previous indexes don't exist, just so that each answer is sort of self-contained. But that's not, you didn't have to do it that way. You could have reused indexes from above, and you should not have lost points if you did that.
How do you want us to do it on the final? Or it doesn't matter as long as we reference it, like we've done this before?
Let's see, I guess my recommendation is to make each problem self-contained, but either way will be fine.
Okay, thanks.
My main reason for recommending that each problem be self-contained is just because it will make it less likely that I accidentally miss something and make a mistake while grading. But yeah, either way is fine. All good questions so far. Any other questions? Okay. So I'm going to switch back over here to our week 13 folder in the repo. And I'm going to scroll all the way down to the bottom now at this very last spot down here. And this is a link to our last big homework assignment in this class, to our search engine problem. So if you click this link, you'll get taken to this repo over here. And we'll spend the rest of today talking about what's going on in this repo and what your goals for this assignment are. So the first thing to note is the due date for this assignment. So this is 2 weeks from now. You'll have 2 weeks to complete it. And this is also the Sunday before finals week. So in this class, the remaining work that you'll have is this assignment here, and then the final. I'll also give you a few more review problems related to the material that materialized view roll-up table material that I mentioned earlier, but that's not going to be a significant amount of work for you. Learning objectives for this assignment. The first one is that for most of you, and definitely probably all the data science students, this is going to be sort of by far the biggest scale project that you have worked on. And so getting more experience working with these relatively large software projects. In this project, you're going to have 14 different containers running at once, and you'll be coordinating all those containers, working together, making sure that they are scraping information off of the web and allowing you to access it all in a good way. We'll be learning to parallelize your data analysis work off the database. So we mentioned last time that in this drawing right here, that the bottleneck for most applications is going to be this database access, because this is the thing that is not stateless. This is the thing that is actually saving information onto hard drives, so that when the program, or when you bring your system down and bring it back up, you get your information back. And everything else, all of these other processes are stateless, so that if they crash, you turn them off, turn them on, it doesn't matter, they'll just pick up exactly where they were and continue sort of processing requests one at a time. And so we want to get all of our expensive processing tasks off of the database, off of the bottleneck, and into these stateless processes. And so we'll see when we talk about this, the design of the web scraper that's connecting out to the Common Crawl database, how we're going to be pushing information, pushing our analysis off of the database onto these web scraper processes. So working with the multi-petabyte Common Crawl data set and work files in particular, this is the file format that the Common Crawl data set is in. And so we'll see the techniques for working with these and processing the information, getting it into the database. We're not going to process the entire multi-petabyte Common Crawl data set because it's just really big and we don't quite have the resources for that. But we'll see how to extract like the information that you care about from it. So you're basically going to pick a couple of domain names like New York Times, CNN, whatever you want, and you'll be creating search engines for those particular domain names. That means you'll have to search through this entire multi-petabyte data set sort of online using a built-in search tool that they have to extract the information that you actually need just for your search engine. And then the last goal, more familiarity working with these indexes to make our queries faster. And then this roll-up tables technique, which again, we haven't talked about yet, but we'll be talking about soon. In order to actually complete this assignment, you won't need to know any of the details about roll-up tables. That this is something that's going on sort of under the hood with code that I've already provided for you. So yeah, you don't have to wait to get started on this assignment. At this point, you know everything that you need to, or at least after we talk about the assignment today, you'll know everything that you need to complete the assignment. So the assignment is divided up into a handful of steps, and you just go through, or a handful of tasks, you go through them just one at a time. And the first ones are pretty straightforward. So just working the repo, and then you'll also need to ensure that you have enough disk space by bringing down all of your other Docker containers and running this Docker system prune command. Again, you only have 10 gigabytes of space on the main hard drive for the for the Lambda server. And if you still have all of your sort of leftover files from the Twitter Postgres and all the previous assignments, then you're not going to have enough disk space to complete this assignment. So you'll need to run this to free up disk space. We'll also, in this assignment, be using that big data folder that you have 250 gigabytes of space to put in there. And we'll see exactly what that looks like here in a second. But make sure not to skip this step, that things will work at the beginning if you skip this step, but then you won't actually be able to complete the assignment. So don't skip these. Task 1, so actually getting the system up and running. There's enough code in this system that it sort of end-to-end works, and you shouldn't get any like error messages when you bring things up. And so we'll take a quick look at the overall structure of things right now. The first thing is that there are 3 Dockercompose files. And yeah, let's go ahead and switch over to the terminal here to look at what the contents of those Dockercompose files are. So right now I'm just in the search engine project folder. This time, instead of having the branch name be master, I've called the branch name HW for homework. But that shouldn't affect anything. You'll just notice that it says HW over here instead of master. There's a bunch of files in here, and we're going to look at these Dockercompose files to start off with. Maybe one trick with Vim that I don't think we've seen so far is how can you open multiple files at once. And one thing you might try to do is something like this, Vim Dockercompose star, like that. But if you do that, you see that it's only one file actually opened up over here. And now if I do :q, it's giving me an error message saying that it can't actually exit. So when I do this, I do Vim and then a pattern matching all the files that I want to open. -p says open each one of these files in a separate tab. Hit enter. And now you can see there are 3 tabs up here opened already for me to work with. We'll start looking at the dockercompose.eml file. And this defines our actual database environment. There are 2 services here, the DB service and the PG service. The PG service is the actual Postgres database. And here you can see that there is a volume right here, which maps on the right-hand side of the colon. This is the information or the location in the container that stores all of the database information. And then on the left-hand side of the colon, this is the location on the Lambda server that is going to map to this location. Here, so $home is your home folder, and then the big data folder and then a search engine folder is where the information is going to get stored in. So right now I'm in project/search engine. I'm going to go cd:/big data like this, type ls, and you can see there is a search engine folder right here that's been created because I currently have running the system, and it created this for me. You'll notice that if I try to cd into search engine like this, I'll get a permission denied error. That it's a little bit awkward working from this folder outside of Docker. If you did want to modify it for whatever reason, it would be much easier to do it through the PG Docker container, doing a docker exec psql or bash command and modifying it that way. But for this assignment, you shouldn't have to modify it at all. It'll just create it the first time and know it's there, but you don't have to touch it. Yeah, so it's inside of this big data folder instead of directly in your home folder, because this is the location, again, where you have 250 gigabytes of space instead of 10 gigabytes of space. I mentioned a long time ago that the Lambda server has 2 different sets of hard drives. It has NVMe hard drives for the main root partition that has your home folders inside of it. So that 10 gigabytes of space has really fast data access. It has the NVMe access. It's basically as fast as RAM was 10 years or so ago. So really, really fast. This big data folder, though, is on HDDs, so spinning Rust hard drives, and so it's going to be significantly slower. If it's just one user using these hard drives at a time, then you could expect about a 10 times slowdown from using the NVMe drives. But because it's going to be more than one user, it'll be all of you working on these hard drives potentially at once. It'll be all of you potentially using them at once. You could expect anywhere from a 10 to a 100 times slowdown in your code from when it was working just on the NVMEs. So you should keep that in mind, that processing might be a little bit slower for this assignment, and so a good reason to not put it off to the last minute. It's one of the reasons why you're also getting 2 weeks to complete this assignment, just to make sure that you have enough time to complete everything. Okay, another little bash trick right here with the cd command. I want to now cd back into this folder right here. This is the folder that I was previously at, but I am lazy and I don't want to retype that folder. I also don't want to move my mouse and copy and pasting it. I'm doing it right now just to show you. But if I was actually working, I would not do that. And what I would do is do cd space dash. And what cd dash does is takes you back to the folder that you were previously at. So this makes it really easy to go back and forth between two different folders that have really weird, or not weird, but different paths, and you can do that quickly and efficiently. It's one of those tricks that makes working with the shell even more efficient. Okay, so that's the PG service. The DB service up here is the PG bouncer service, and for DB, this is the service that the everything is actually going to be connecting to. You'll never connect to PG directly unless you're doing some sort of administrative task on the database. You'll always want to be connecting to the DB service, because PG bouncer will ensure that basically you're not overloading the database, and that if you had multiple versions of the database, it would automatically spread out your connections to all those different versions. So all the connections will go to DB and not to PG. You'll see right here that we have this .env.production file. So this contains the tabby.env.production, all of the information for the security information for the database, in particular this password over here. And again, this is a file that's not going to be uploaded to GitHub, either in my repository or your version of the repository. And so you'll have to create this password for yourself. In order to automate that process a little bit, so there are good test cases for this repo that are already pre-configured to be passing. And one of the scripts that's part of that, so they're all located in this scripts folder down here. If we do ls scripts like this, then here is the test cases, and here is a script that will automatically generate a new production environment for you with new strong passwords that nobody has ever seen before. And real quick, take a look at that file, createpasswords.sh, and it's yeah, the details here aren't super important, other than this password is being randomly generated every time. And so when you first get this this repo and get it on the Lambda server, in order to actually bring up the run Dockercompose, bring up your services, you'll run this create passwords. It'll generate a new password and create this environment file for you. Any questions so far about any of that configuration issues? Okay, so Dockercompose, again, has the databases, and then this Dockercompose override and Dockercompose prod has the actual web server configurations. So Dockercompose override, this is the sort of the test environment where make modifications to the Flask app, and it automatically brings those up. It only has the Flask app running, and then the production one, it has Nginx and sitting in front of the Flask app, and then using Gunnicorn to actually serve it. So much more efficient, but harder to develop with. One of the things that you'll have to do is change this ports value right here for the on this override file. That on the previous assignments, you had to change the ports inside of the databases in order to be able to connect to the databases from the Lambda server. In this case, there's only one database, and you're not going to have to connect to it directly. So there's no ports to change related to the database. But you will have to connect to this web server in order to be able to see your search engine results. And so you have to change the ports here in order to do that. And just like before, that's to the left of the colon, change that number. And then also in order to be able to access the access your web server, when you SSH into the web server, you'll have to do it with the port forwarding, which if you're on either Linux or Mac is that -L command to enable port forwarding. If you do all of those steps, then, and those steps again are listed right here for you to reference. You do all those steps, then you should be able to connect to the server, and it'll be localhost : whatever port forwarding number you select, and then you can type in whatever you want to search for, and there won't really be any data yet because you haven't actually loaded data yet. You just have your system up and running. In this case, I've loaded just a few websites for us to see some examples with, and so they're here, but you won't have anything at all yet. Let's see. Last thing to do just to make sure things are working is to run that check endpoints script, this one right here. So copy and paste that here, and you should get that they all pass. And if you do that, then you know that your system is like set up, ready to go, and you're ready to actually start the work. Any questions on the setup? Okay. Then there's the next task. Task 2 here is loading data, and it's divided up into two parts: task 2A and 2B. 2A does not require any programming. It's just getting the Docker containers up and running and doing their thing correctly. And then 2B sort of extends 2A to not only get your Docker containers up and running, downloading things off the web, but also doing some programming to process the work files in an efficient manner. The, let's see, so in 2A, you'll develop the service downloader work, and 2B, develop the service downloader host. Downloader work will download an entire work file. So we'll talk about exactly what that is here in a second, but basically 100,000 or so web pages that are part of like one small chunk of the Common Crawl or the Internet Archive. Downloader host, rather than being sort of a random collection of things that happen to be scraped near the same point in time, you would say like, okay, I want everything from New York Times, and it'll download just things from New York Times to make your search engine like effective for certain particular domains that you're interested in. And that's the part that making it specific for a particular host, that's the part that you're going to be implementing. So for this downloader work, we're going to first take a look at the Common Crawl, how it's formatted, what these work files are, and then we'll take a look at the project itself. So coming up over here, this is commoncrawl.org. This link right here takes you to the same location as if you go to commoncrawl.org and then the data get started. And this is the big list of like what their data actually is. You can see that at the beginning, they started collecting data back in 2008. Make this a little bit bigger. And then they've continued collecting data up until the present day. And they've greatly increased the pace at which they have been collecting data. So way back then, you can see one of these sort of segments corresponds to a whole year or a whole quarter. And then down towards the bottom, they're getting down into like month sort of fidelity. And each one of these links takes us to about 80 terabytes worth of data. So it's the same amount of information per link. Let's see, we'll just click on this one semi-randomly and come down here. And these are the all the information related to all of the web pages that the Common Crawl scraped during January 2021. The files that we're going to be most interested in are the work files. These are the actual like raw archives of what has been downloaded. These WAT files contain sort of just the metadata about the crawl, and these WET files contain just the text of web pages contained in the crawl. On the right-hand side over here, you can see that so the compressed size of these sets of files, 80 terabytes for the work files, so that's the full thing. The metadata is 20 terabytes, and then just the text itself is 10 terabytes. The reason these two things here don't add up to a full 80 terabytes is because the crawl also contains things like images and PDFs, things that don't make the cut to get into these files down here. We talked a little bit about robots.txt files last time and what their purpose is in web scraping. Again, basically they show what things are allowed and not allowed to crawl on a web page. And if you look at only the robots.txt files, that's about 230 gigabytes of information. So we saw it before, those are text files, super small, but there's one for each domain name, and there are approaching billions of domain names that have been crawled. And so that's why it's still 230 gigabytes. So it's a lot of information here. I'm going to click on this link right here. And this link does not take me to the full 80 terabytes of information. Instead, it's just a small file, like less than a megabyte, that contains a list of all of the paths to actually download the raw data. And let me make this a little bit bigger, real quick. There we go. There we go. And so inside is just a list of all of these actual work files. And here is the URL or portion of the URL to get the work files. Each one of these individual files is about 2 to 3 gigabytes in size. And I'm going to real quickly go to the end of the file. So Shift G and Vim, there's about 80,000 of them. So that's where the actually, I guess it looks like in previous iterations, there were 2 to 3 gigabytes in size. These ones are only 1 gigabyte in size. And so that's why there's 80,000 gigabytes or 80 terabytes. In order to, let's see, for this work downloader assignment, you're gonna have to pick one of these work files. It doesn't matter which one, whatever, select a time frame that's interesting to you. Each one of these work files is going to just contain a huge smattering of different websites that happen to be crawled at these timestamps right here. So if you read this, this is year, month, day, minutes, or hour, minute, second. And so these are all of the things that were crawled at this particular second of their crawl. And you pick one of these URLs, and I'm going to go ahead and, let's see, I'll copy that, quit out of this, quit out of this. And in order to actually access this file, you have to take, where did it go? This link right here. This link right here, commoncrawl.s3.amazonaws.com/, and then paste that file to the end of this. And that gives you the full URL to this work file. Come back over to, oops, here. There is a script, download work.sh, that you can run with that full URL to the right of it, and it will open up a new container for you and do the downloading and processing. You'll have to do that with 5 different of these work URLs, just so that you can seed your search engine with a fairly decent number of URLs. Come back over here, and so going to, there we go, open up pSQL connecting to the database. I just ran one of these work URLs through the system before class, so we can see what the expected results is going to look like. And at the very bottom down here, I give you a handful of queries that you'll have to run on your database, these queries right here, in order to know like how much data has been ingested into your system. So the first one is this query right here, select count star from meta HTML. This meta HTML table is the sort of main table that's going to store 1 row per URL that you've downloaded. So come down here, select count star from meta HTML. So it's downloaded 17,000 URLs. And that's 1 full work file's worth. So about 1 gigabyte or so stores 17,000 URLs. Then there are, let's see, so this roll-up insert, come down here, run that query, and it tells you for every hour that you've been running, how many URLs did you download just in that hour. This host field tells you how many domain names or host names those URLs come from, unique host names. So 9,500 different unique domain names were crawled during this hour. And then host path is the host name slash whatever particular URL in that path. So there's about 1,000 or so URLs that that duplicate different host names. And then over here is the total number of URLs downloaded during that particular time. Let's see. This query right here will show us the actual URLs themselves, or the host names themselves, how many pieces of information that you've downloaded from each of those host names. So host is the actual domain name, and you can see that these are in sort of a relatively weird format. We'll talk about why that is here in a second. And then the host path, again, is the total number of URLs from that particular domain name. The formatting of these domain names is it's very common formatting that you'll see pretty much anytime you're working with large-scale sets of web pages, and it's in reverse order from the normal way that you would write out a URL. So this URL, or this host right here, I'm just gonna paste that here. That's equivalent to articles.orlandosentinel.com. The reason for doing it in reverse order is it makes sorting actually be meaningful, that these, so if we had multiple subdomains off of the Orlando Sentinel and we sorted them, they would all be right next to each other. And we'll see that here in a second. Yeah, it's a big project. Again, one of the goals of this assignment is to get you familiar with these sorts of big projects. And when there are these big projects, there's just so many interconnected things that there's rarely just like one linear path through that you can take to fully understand what's going on. And you have to bounce back and forth between different concepts. So we're gonna focus next on understanding this URL format and how that relates to your task 2B right here. Maybe before we do that though, I'll stop and see if anybody has any questions about anything we've seen so far. Okay, so in task 2B, you'll basically be modifying the code in the download work in order to be able to download information from an individual web page. And the first thing that we have to do is figure out which web pages might you want to download information from. And that's what this query right here is going to tell us. So come over here, quit out of this, run that query. And here are all of the host names, domain names that I can guarantee that all of this software will work for. These are the host names that I have test cases that people have gone through and manually looked at and verified that it's able to correctly extract information out of those web pages. And so I'll just go to the bottom of this real quickly. You can see there's about 2,000 different domain names that work here. And now we can see sort of why you might want to have these things sorted in reverse order. But here, for example, we have the .co.uk extension. So these are like .com websites, but specifically for the United Kingdom. And now they're all nicely grouped together right next to each other like this. We even get to see that the BBC and the BBC.news websites get grouped together like this. So it's much more convenient than if they were sort of spread all apart. We can see exactly how many subdomains each domain has. If we looked at, for example, LinkedIn, let's see. Well, yeah, you can see, so here's all the Perus grouped together, orgs grouped together. So it's just a little bit easier. And so that's why people write things out this way. You'll have to find 5 of these domain names that you are interested in for whatever reason, and those will be what you do for processing the ones that you'll run the assignment on. In terms of what you have to actually do for the assignment, there is this file right here. So services/downloaderhost/downloaderhost.py has 3 fix me statements inside of it. So here we have this services folder. Again, services contains one folder for each of the services that's going to be run as part of this system. The downloader work and the downloader host, we're going to have multiple instances of these services running. So even though there's only one folder here located for them, we'll have 5 of each of these. So that'll bring us up to a total of 13 different services that you'll have running at once and coordinating with each other. And now if we go services/downloader host, here's the Docker file inside of here, and then this downloader host.py file. And so let's open that up. And / to search, fix me. Here is the set of code that you'll actually have to write. So the information, basically the purpose of this code here is to extract information out of these work records, extract the information that you'll be needing in order to insert it into the database. And then the actual puts all that information here into a list of dictionaries, and then there's this bulk insert function that does the inserting for you. So you won't have to write this code. I've written this code for you. The main thing that you'll be doing here is working with these work files and extracting the information from the work files. Let's see. In order to do this, extracting information from the work files, there is a Python library that we'll be using called the Cdx Toolkit. Come over here. Cdx Toolkit is the name of the project. And I'll show you a little bit how to use that next time in class, but mostly I'm going to be expecting that you'll be able to look at the documentation for this project and figure out the information from here. Plus, you'll also be able to use the downloader work as a reference. So the downloader work is fully implemented for you. You don't have to change anything in here. And down here, there'll be a corresponding location where it's doing this, this insertion for you, this process work from disk function. And this is the equivalent similar section of code that you can use as a reference right here. Let's see, I think, yeah, this is a good stopping point for today. So we'll continue talking about the assignment next time, some last bits of details, and then talking about these roll-up tables starting on Wednesday. Any questions about anything? Okay, well, if anybody does have questions, I'll stick around for a little bit, but otherwise I will see you all on Wednesday.